Even this this little here forklift. So you had your FG, you had your FN, you had your displacement forward. Notice it's perpendicular. FG, F, you can call it FN, or you can also call it F, forklift. And well, what's changed? Well, all the works here, the forces are perpendicular. It's at a constant velocity, so the F net is 0. And you'll find out here that, of course, all the works are 0, so what's going to change? None. Nothing. All right, let's go up here. Let's go to the spring. Let's get something where something is actually changing. So if you notice here, well, this one, there is going to be some work done on the spring. It's going to be that average force of the spring times that compression. And what has changed, well, a few things will change about this, but the simplest thing, there's going to be WS, which means there's going to be a change in the PES. So you see here, when there's work actually done, the energy changes. When there is no work done, which is all these were set up here trying to get you tricked, either it sits still, constant velocity, and orbit, uniform circular motion. You know, all those, there's no work done, so there's no change in the energy. If we go back a page, oh yeah, these we had some business. 15B, this was frictionless. So in this case, if you noticed, there was a drop in height that aligned with the FG. And so there was definitely WG here. And this thing, based on the FG parallel, FG perp was this way, FG parallel pulling down the ramp. Of course, you get your normal force over here. Might as well label them all in. FG perp over here, and that was it. Hash out your FG. FG parallel is going to be your F net. And W net is not going to be 0. W net's going to be something. WG is something. And so what's changed here? Well, since there is WG, there is going to be a change in PEG. And there is. It loses height. And since there is W net, there's going to be a change in net force. Remember, the way to remember this one, F net means that there must be acceleration. And acceleration, of course, means there must be some sort of change in velocity. And of course, that change in velocity then connects with a change in kinetic energy. So I know net and KE, they don't exactly match the way the others do, but worth remembering. So these two types of energy change. So when the type of work happens, the type of energy that aligns with it changes. So I know this feels a little slow for some of you. That's okay. Listen, pause it if it's fast, skip ahead a little if it's slow. Just look at what I've written up. But it's worth going through this right now to make the connection. Work, energy. The type of work causes the type of change in energy. This one, all right, let's check this one out. Change the color. Why not? This one, you have a rough incline, you have a constant velocity. Constant velocity means your F net is 0. Means your W net is 0, which of course should tell you there's no change in kinetic energy. However, there is a displacement that anti-aligns with the FG. So there is going to be WG done, which means there is going to be a delta PEG. The normal force is actually perpendicular to the true displacement, so that one's not going to do any work. But it's pulled, so you have this external force right here. I'll just call it F. That one is going to do some work. And this, let's see here. We could break the FG into components, but let's leave that out right now. Let's just put our FF down here. You want to do the whole free body diagram, you could do that later on, or actually you should have done that already, pardon me. FF, there is work done against friction, which means there's going to be a delta Q. Oh, you remember talking about that Q way back when? All right, cool. Let's keep going here. We'll start moving a little faster. And actually working backwards is not bad because we're getting to the more common scenarios here. This one. So sled rider, we got a constant velocity. So the net work you know already is 0, which means there's no delta KE. But of course there's no delta KE. It's at a constant velocity. What else you got? There's no WG. It's perpendicular to the displacement. Displacement's here to the right. There's no WN. But there's definitely some friction here. So you're going to do some WF, which is going to cause a delta Q. So interestingly, the total energy of this box is going to, well, its PE stays the same, its KE stays the same, its PES stays the same, but it's being dragged on a rough surface. It actually gets hotter. So this thing actually does increase total energy, and, well, no surprise, this one's applying an outside force. That's where that extra energy is coming from. All right, this one, same sort of game plan as we've been doing. So box pulled along level frictionless ground to the left. So here was your F external. You had your FG, you had your FN, it's frictionless. There is a net force here. It's the F external, which means there is net work, which means there is a change in KE. Well, that makes sense, because if you pull a box with no friction, it is going to change speed. It is going to speed up. And or if it's already moving to the right, it'll slow down, and you get a change in KE. This one up here, we have everything already drawn in here nicely. Well, the handwriting's much better, I'm sorry. Try to type these in clean. The free body diagrams you have already. The change part is the part try to clean up. All right, so what has changed? Here, WG 0, all these are 0 except WF. So there will be a change in Q. And also, there's a W net. And since there's a W net, I'll write it over here, there is a change in KE. Why, in fact, yes, both of these things do occur. It heats up and it slows down. In fact, those two change by the same amount in this case because there is no external or outside force here. The total energy of this scenario is conserved. The mechanical is not, however, because a lot of it's leaving to heat. All right, let's go back to 16. Maybe there's one or two down here. All right, skydiver falling freely. Well, we got WG. So there's a change in potential energy. We know that. You can see that. There's also a W net. So there's a change in KE. Cool. This box being lifted, there's a WG. So there's a change in PEG. Pardon me. And there you go. No W net. So that's that. All right. The only other one we had in here was back to page 12. And we said not yet. You can fill in these not yets now. These are basically just what we saw in that chart on the bottom of page 23. So delta PEG, we're just writing out that equivalence, is FGD, really DY, which is WG. Here, delta KE, that was F net D, that's W net, also known as W to accelerate. It's just like a little practice page. That delta PES, that's that 1/2 kx squared. I mean, you could write that too. It erased. Fantastic. I didn't think it would. Let's clean this junk up. Yeah, it's written in slightly different order than I wrote it, but that's okay. Yeah, look at that. So nice. I didn't think the erasing would work. There it is. And then WF is FFD, which is delta Q. So there is a way to calculate delta Q. Now, I know you're probably looking at this and you're like, yo, where are you going with all this? Don't worry. Let me show you where I'm going with all this. The actual problem solving, back to page 24, you will see is pretty straightforward. So don't get crazy here. Just let your givens do the talking. Seriously, let your givens do the talking. So if you check this out, Question 46. Now you can run ahead of me on these. You could slow down. You can pause. Whatever you need to do to make this work for you. But you'll see it's a pretty straightforward process. I'll probably run one or two, and then I'll just start setting givens, and I'll type the whole thing up. You can look at it. So here, be real careful with your... I wish I could yell givens with units. I might get in trouble waking everybody up in my house. All right, we can do it quiet now. You ready? No. Givens with units. Go ahead, do it. It's kind of fun. All right, this one asks for the change in potential energy, something that's lifted. So they're talking about delta P E G. That's what they want to know. Now, honestly, it's not a bad idea for you to immediately zoom a little more, give us a little more room to write. Immediately write an equation for it. Now, there's really two ways to go with it. You could say, all right, delta PEG, kind of the standard way is mg delta H. Cool, I'm down with that. However, if that does not match your givens, you may want to try another one. Let's see what the rest of our givens are. All right, so it's lifted from 2 meters to 7 meters. Now, don't get fooled here. What they're telling you is the initial height is 2 meters. I'll write it up here. And do a little sloppy on sig figs just because it's not so easy to write. The final height is 7 meters, but you do understand neither of those are a delta H. Delta H is 5 meters. By the way, delta H is the same thing as D for displacement. So it's not 2, it's not 7, it's 5. And it's lifted by a force. Technically, the force, that's the external force, is lifting this thing. 20 Newton external force, and they say a steady speed. So a steady speed right here means that the F net is 0. Now, you could probably just throw some numbers at this and get it right. However, there is really a right way to do this, and the right way to do this is with a free body diagram. So if we got a free body diagram, we come over here and we put this little box. That little box has got itself a little there, FG, pointing down. It's got itself a little there, F external, pointing up. You know these two are the same because it's got an F net. Look at this, nice, getting the colors right and all that. F net is 0. They said at that steady speed, straight up. And so you know that the F external, they already told you is 20. And then the FG, 20 newtons. The FG must also therefore be 20 newtons. Now that's really all the given you need right there. You know FG. You know the change in height or the displacement. Boom, you're good to go. Now, you could easily figure this one out. You know, it's not much magic to say what I'm about to say, but it's worth your recognition that, well, wait a minute. Is there another way to look at the delta PE equation? And the answer is yes. You could say, oh, well, this is also equal to WG, which is also equal to FGD. Really dy, but even if you forget about that, you'll be okay. And if you notice here, well, that's kind of nice because we've got FG, we've got D in the Y direction. That fills this perfectly. Solve for WG and you get delta PEG. That's really it. That's all this is saying, is that you just have another tool to attack these problems.